Thank you for the introduction. I'm going to talk about the main subject of my PhD thesis, which is done in collaboration with Mercedes Martin Benito and Javier Olmedo. And it's on observational consequences in Loop Quantum Cosmology. And it's a bit in line as in the first talk of this session. So it has to do with cosmological perturbations in the specific context of Loop Quantum Cosmology. So for anyone who is not familiar, Loop Quantum Cosmology is a particular approach to quantum cosmology, and it is based on techniques of loop quantum gravity, and it applies these techniques to cosmological models. And the main result that is relevant for my work here is that the Big Bang singularity is resolved in terms of a quantum bounce that connects a contracting epoch of the universe with an expanding one. So in these settings, we have the volume connects a contracting universe with an expanding one, and it never goes to zero, has a positive minimum, until the energy density is finite, never diverges, has a maximum, finite maximum. And so the point here is that we have well-defined pre-inflationary dynamics, and this may excite perturbations even before inflation begins, unlike in standard cosmology. So in standard cosmology, usually what is done is that we fix the vacuum of perturbations at the onset of inflation, and that's because shortly before we have the Big Bang singularity. In quantum cosmology, we have, before inflation, we have in these models a period of kinetic dominance. So right after the bounce, we have a very short, very fast inflation, superinflation, a period of decelerated expansion, all before inflation, standard slow roll inflation begins. And so the idea is that this difference in the background may affect the dynamic of perturbations because they may reach the onset of inflation in a state that is not the Bunch-Davies vacuum of standard cosmology. But besides this, we also have corrections that come from quantum cosmology to the equations of motion of the perturbations. So both of these may have an effect on the primordial power spectrum, which is the power spectrum of cosmological perturbations at the end of inflation. The exact shape of this primordial power spectrum depends on our model, so it depends particularly on the choice of vacuum. But in any case, in quantum cosmology, it will depart from the near scaling invariant power spectrum of lambda CDM for infrared scales. So for scales below a characteristic scale of the theory that I call KLQC. And that is because more energetic scales, so short wavelengths, will not be affected by these differences in curvature. So quantum cosmology actually affects the infrared part of the power spectrum. So then the question becomes on whether these effects can be in the observable window, or whether we don't see anything and it's perfectly agreeable with the power spectrum of lambda CDM. And this has to do with parameters of the theory. We have a parameter in particular that gives us longer or shorter inflation. And if we have too much inflation, then this scale is shifted away from the observable range, and we have no visible effects. So this is what we want to explore. And to do that, we need to deal with the choice of vacuum. And this is a choice because in quantum cosmology, we don't have enough symmetries to define a unique vacuum, as is usual in quantum field theory in curved spacetimes. And so there have been a few proposals in this regard within the context of quantum cosmology, from adiabatic vacua to the diagonalization of Hamiltonian, to minimizations of quantities, some instantaneous quantities and some smeared quantities. One of these is states of low energy, which minimizes the energy density when smeared in a given time window. And another one is the non-oscillatory, what's called the non-oscillatory vacuum, which is the one I'm focusing on in this work, in this presentation. So the non-oscillatory vacuum is a vacuum that can be computed by minimizing oscillations of the perturbations in time, from the bounce to inflation. And this results in a power spectrum which has minimal oscillations as well. So the power spectrum in this case is just the near scale invariant one with a power suppression and some minimal oscillations. And the fundamental motivation to consider this vacuum is that we can say that these oscillations are spurious and they're spoiling the effects that are coming from the bounds. So we want to get rid of them so that we can just consider these effects. But also additional to this, this same power spectrum can be obtained from the states I mentioned before, states of low energy in a given configuration. And many power spectra that come from loop quantum cosmology, from the vacuum that I mentioned before, have some kind of power suppression at infrared modes. And so this is a nice situation to start with, because any power spectrum that has this kind of behavior will lead to the same results that we're going to show here in principle, or it has the possibility to lead to the same results. Okay. Okay. So, so at the end of inflation, we have the primordial power spectrum, which I show here. But this is not what we observe today, because this is at the end of inflation. So to compare with observations, we need to evolve the primordial power spectrum until we get the CMB, the cosmic microwave background, in particular the correlation two-point correlation function, which is usually shown in this way in terms of multiples. And to do that, we are going to consider standard cosmology. So we don't expect loop quantum cosmology to have an effect here, besides the effect it already has in the primordial power spectrum. Okay, so we're going to start simple. So we're going to parameterize this primordial power spectrum just to simplify computations. Actually, the slope of the suppression and the amplitude of the oscillations does not change in our model with our parameters, so we're going to fix those. And so this leaves us essentially with three parameters: the amplitude of the power spectrum, the tilt in the nearest scale invariant part, and both of these are already present in lambda CDM. So the only new parameter we have is actually the scale at which this suppression occurs. And this will parameterize, will encode all the relevant information that comes from loop quantum cosmology. Essentially, this is related to the parameter that gives more or less inflation, as I said before. So our model is in fact a seven-dimensional model with 7 parameters. 6 of those are already considered in lambda CDM, and then we have the extra one, which is KC. So what we're going to do is explore the whole parameter space. We're going to compute posterior probabilities, which are the probability distributions for each parameter. And if we do that, we can find this posterior probability of our important parameter KC. So this is just, as I said, a probability distribution of the parameter, which means that a peak in this distribution means that this value of the parameter gives us the model that best describes the data that we compared it with. Okay, so usually a posterior probability of a parameter is something like a Gaussian. This is not, but it makes sense that this is not, because so first of all, we have a cutoff here, and this is artificial. This is just because we need to give a minimum value for KC. And we'll see that this is not relevant because this whole region here gives us a power spectrum that is completely agreeable with lambda CDM, and it would not change if we consider lower values of KC, because it essentially gives us a power spectrum that in the observable part, in the observable range, it's exactly lambda CDM. So it makes sense that this is a plateau. These are all equally likely values for our parameter. And then we have that with the value at the peak here, we have some suppression already within the visible range. And we see that it is big. So the data is actually preferring that some of the effects are observable. However, then we have a sharp cutoff, which means that some of the effects can be observable, but not too many. So in the next few slides, we're going to see what this implies by fixing values of KC. And actually, we're going to consider these three that I'm showing here. So one that is essentially lambda CDM, the one that corresponds to the peak, and one that just is like the maximum observable effects we can have within the observable window, just so that we can see what the effect is of introducing this KC gradually. Does this work? Yes. Okay, so I'm going to talk about two anomalies which are alleviated with these models. The first one is the lensing anomaly, which we also heard about in the first presentation of this session. And this anomaly is found through in the Lambda CDM model through a consistency check. Basically, we introduce by hand a phenomenological parameter, which is this AL, which is the lensing amplitude. It controls artificially how much the CMB is lensed from the surface of last scattering till today, which means that if AL is larger than 1, then it's lensed more than we would expect in Lambda CDM. If it's less than 1, then it's lensed less. And the consistency check is to consider the model of Lambda CDM plus this parameter, let it vary, and see what the data tells us about this parameter. And the data tells us that it does not prefer it to be 1. Actually, at 2 sigma significance, which depends on the choice of data, but it is an anomaly that is there. And furthermore, AL can be consistent with 1 if we let curvature vary as well, the curvature of the universe. And then the data prefers the curvature to be negative, so closed universe, as we heard in the first talk. And then this leads to some other inconsistencies. This has been labeled a crisis in cosmology. But loop quantum cosmology can have an effect on this as well. Okay, so in loop quantum cosmology, what happens is that I mentioned we have 6 parameters of Lambda CDM also in our model. Most of them, the best fit of those parameters is not affected, except for essentially 1, which is the optical depth at reionization. And so that's why I'm showing the plot here in the AL tau projection, because since loop quantum cosmology affects the best fit of this parameter, and this parameter is anti-correlated with AL, then we can see that these regions, 1 sigma regions, are shifted such that AL equal to 1 can be within the 1 sigma region. And all that happens is that we have a different best fit value for the optical depth. And this is the least constraint parameter of the 6 of Lambda CDM. So for now, this is perfectly acceptable. And in the future, further observations of this parameter can help us constrain actually loop quantum cosmology in this way. But the point here is that we don't need to affect physics of the lensing from the surface of last scattering to today, because this is a consistency check. This parameter is telling us that something in the theory was not consistent, and we don't have this level of inconsistency in loop quantum cosmology with this choice of vacuum at least. Okay, so the second and last anomaly I'm going to refer to is the power suppression anomaly, and this is the fact that the 2-point correlation function, which I'm showing here, the angular correlation function, is remarkably consistent with 0 for large angles, so it dances around 0 here, whereas the Lambda CDM model does not predict this to be as close to 0 as it is. This is actually quantified best in this integration of this function. And you can see that in Lambda CDM, this prediction is about 35,000, and the observed values is about 1,200, or if we consider full sky data, so reconstructing the bit that we cut out from the galaxy contamination, it's a little higher, but it's still very far from the values of Lambda CDM. So this would correspond to an unlikely realization of a Lambda CDM universe. How unlikely? Then we would have to consider the distribution of this parameter. So in a Lambda CDM universe, we perform many realizations of the model, and we see how many of them turn out to have such a low value, at least as low as the observed one, which I'm showing here. So what you can see is that in Lambda CDM, the observed values are in the tail end of the distribution, which means that they have small p-values. And in loop quantum cosmology, this distribution is shifted to lower values, and the variance doesn't change much. So this means that these values are not in the tail end for loop quantum cosmology, and they don't correspond to as unlikely realizations of a loop quantum cosmology universe as they do in Lambda CDM. And so in this sense, the anomaly is alleviated. Okay, so just to conclude, the effects of loop quantum cosmology show up in the infrared part of the spectrum, always. And actually, if we consider models that give us a power suppression, the data actually prefers this suppression to be a little bit within the observable window. And this can have actually important effects, as I just showed, because they can alleviate tensions that have been observed in the data. And so what we want to do in the future is then consider the other forms of power spectra that can be found within Loop Quantum Cosmology, which don't have just power suppression, but also power enhancement, which will have a different kind of effect. So thank you now for your attention.
Okay, time for questions now. We have one there. I'm scared. Okay, yeah, it's very loud. Thank you very much for the talk. I was just wondering, so it's in the conclusion, so maybe I don't know if you have any intuition about it, but so the other vacua are like, do they introduce many other parameters? Like, would they be more complicated? Yeah, just wondering if this was like one of the simplest vacua you chose and what you expect for the other.
Yeah, this is definitely one of the simplest vacuum you can choose. I mean, in the sense that the power spectrum is simpler to parameterize. The other vacuum would have, they typically have power enhancement as well as power suppression. So you would have a few more parameters, the scale of power enhancement, the slope of power enhancement, and all that. So yes, and these would then relate to the parameters of the theory.